Hello everybody, this is Unit 4 Covalent Bonding and IMFs. We're going to start off with just doing the basics of covalent bonds and polarities. And what I like about this starting picture is that it really does what we did in our Venn diagram, where it's comparing the difference between ionic and covalent. So on the right hand side over here, we have our ionic bonding where it's transferring that electrons and it's forming ions. But in covalent bonding, notice that it doesn't do that. For covalent bonding, we have those sharing of electrons, and they're going to be mutually happy. They do not form ions. That's going to be really, really important that we have a sharing versus a transfer. And the reason why covalent bonds are attracted to each other isn't because of opposite charges from the ions. It's going to be about the attraction from the valence electrons to the nuclei is really what's going on there. So we kind of went over this a little bit in class, but covalent bonds form between two nonmetals, that's really, really important, by sharing their electrons. Both elements are nonmetals, so they're both trying to gain electrons to fill their energy levels. And so since neither one of them wants to actually give up any electrons, they come to like a happy place, a happy median, and a compromise, if you will, and they decide to just share them. So during this process, we are not actually gaining electrons, we're not stealing them from other atoms, so we're not forming ions. And because we don't have ions, we don't have any flow of delocalized electrons, these do not conduct electricity at all, ever, not as solid, not as aqueous, not as liquid. They do not conduct electricity. So typically what we're going to deal with is a single bond. So if atoms in a covalent bond share 2 electrons, we consider that to be a single bond, and we represent that with this one little line here. So these are our single bonds. We've got a single bond between hydrogen and hydrogen right here on the left, and we have a single bond between chlorine and chlorine right there on the right. Okay, these are 2 molecules, both containing single bonds. So this hydrogen is sharing an electron with the other hydrogen, and that's represented by this, and that means 2 valence electrons per line. But atoms can share more than 2 electrons. If we see in our O2 molecule in B, O2, oxygen gas, that's sharing 4 total electrons. So there are 2 bonds, there are 2 bonded pairs for a total of 4 electrons shared between them. And then over and into here, we get a triple bond right in the middle. That is 3 bonds, or 3 bonded pairs, for a total of 6 valence electrons. And if you actually hold up a rubber band, and we'll do this in class, if you hold up a single rubber band or a hair tie or whatever, you can pull that thing pretty darn far. But if you have 2 or 3 rubber bands, it's really harder to pull them apart. And so what we start getting into is this idea of bond strength, or the energy required to break these bonds, because that's really what a chemical reaction is. A chemical reaction breaks chemical bonds. So we start off with our single bond here. Picture this as your single rubber band in between 2 fingers. Okay, that's pretty easy to break. But if you have 2 rubber bands on your fingers, that gets a little bit harder to break. So the bond itself is going to be stronger. It's going to require more energy for you to break it. And the strongest type of covalent bond would be our triple bond. That's 6 electrons that these things are sharing. They're really kind of tied together by those 6 electrons that they're sharing, and therefore it takes a lot of energy in order to break a triple bond. So we got our covalent bonds. Nonmetals don't always share electrons evenly. Some are greedy. This is going to tie back into our electronegativity. Remember, some nonmetals are more electronegative than others. Some are better at gaining electrons than others. So there's 2 types of covalent bonds. We have something called a nonpolar covalent, and we have something called a polar covalent. You guys have all told me that water is a polar molecule, but you don't really, at this point, probably understand why. So a nonpolar molecule contains covalent bonds, and these covalent bonds, the electrons are shared equally within that bond. So if we look at this picture here, up in the top right. I'm going to look at, why is this not drawing? Oh God, there we go. Okay, this is a picture of a nonpolar covalent bond. So the yellow or the orange color is showing the electron density, where the electrons are kind of going to be. And notice that the electron density is symmetrical, it's even, it's being shared evenly between each hydrogen. That's because they're the same electronegative. They're pulling on those electrons the same amount. But then when I go over to this polar covalent over here, I have hydrogen and I have fluorine. We know that fluorine is super electronegative. It's gonna, like, think of this like a tug of war. Fluorine is pulling those electrons really hard close to it because it's really electronegative. So that's why this side is a darker orange. It's pulling the electrons closer to it, and hydrogen still has those electrons. They're still sharing them. They're just not being shared equally. So a polar covalent bond has an unequal shared valence electrons, where the electrons are being pulled more towards one atom over another. And this happens when we have a difference in electronegativity, when we have one atom in the bond that is really electronegative. So think about water. So you all said that water was electronegative, or you said that water was polar. Okay, so if I have H2O, you can probably tell me that oxygen is more electronegative than hydrogen. So oxygen is going to pull these electrons up close to it. So if I'm going to draw this slightly different, I don't like the way I drew this. Okay, if I'm going to draw these all as dots, oh my God, everything's awful. Okay, here we go. If I'm drawing these all as dots, oxygen has its lone pairs, cool. And now we're talking about the pair shared between oxygen and hydrogen. So oxygen's going to pull that pair really close to it. Sure, it's still being shared with hydrogen, but do you see how much closer it is with the oxygen? That's kind of what's happening. The oxygen is pulling it really close to it. It's still being shared, but it's going to be closer to oxygen than to hydrogen. That's what causes this polar bond. So there's a way that you can do this. To determine bond polarity, you actually need electronegativity numbers, which you have on your placemats. And you're going to do some basic math. You're just going to be subtracting. First, you need to figure out what the electronegativity value is on your placemat, or on the next slide. And then you're going to find the difference between it. If the difference between the electronegativity is 0 to 0.5, then we're going to consider it to be nonpolar because they're pulling the electrons about the same amount. If the electronegativity difference is between 0.6 and 1.8, then we're going to consider it to be polar covalent because one atom is pulling on those electrons really, really hard. If we get a difference greater than 1.7, then we're going to consider it to be ionic. And that's because one atom pulls the electrons so hard that it actually removes them from the other atom. That's what causes an ionic bond, because of this difference in electronegativity. So here is your bond polarity or your electronegativity chart. This is where you're going to be looking. There's one on the back of your placemat that you get on your tests. So if I was going to be doing this between magnesium and chlorine, you're going to look at each magnesium and each chlorine. So we are not to the point yet where I can do this all together. So we know that magnesium has some attraction between chlorine. I don't like the way I drew this. So this is an ionic bond. And we know that already because magnesium is a metal and chlorine is a nonmetal. But we need to prove that based off of the electronegativity differences. We know that this is what that looks like based off of last unit, but we need to prove that with your electronegativity differences. So we're going to look just at the bonds right now. We're going to look at the bond between this magnesium and this chlorine, and the bond between this magnesium and this chlorine, and they're going to be the same. So I'm going to find the electronegativity of each. So we're going to find the electronegativity of magnesium, which is 1.2. And we're going to find the electronegativity of chlorine, which is 3.0. So the difference between there is 1.8. So since the electronegativity difference is so big, it's going to be so high for chlorine that chlorine actually rips the electrons off of magnesium. And that's why this is ionic. It's not just because it's a metal and a nonmetal, it's actually because of this electronegativity difference. So this is just kind of a flashback to last unit, and then we're going to do some examples where it's two nonmetals, and you'll see it being nonpolar versus polar covalent. So for this one, we got H2O, hydrogen 2.1, oxygen 3.5. We get a difference of 1.4. If you look back at your ranges, always refer back to your ranges, that would be considered polar covalent because oxygen has a much higher electronegativity than hydrogen. So there's another way that we can show this visually. We can show that the electrons are being shared unequally, and we can know they're being shared unequally based off of our electronegativity differences. But once we know that they're being shared unequally, we can draw something called a bond dipole or a dipole vector. And what you do, it's this little arrow with a plus sign at the end. And the arrow, we use it for each individual bond. The arrow shows on this side of the arrow, there's a plus sign. That means that that side is going to be a little bit positive, and it points to the one that is most electronegative because the dipole vector is really showing us where the electrons are closer to. So because chlorine has a higher electronegativity, it's pulling the electrons closer to it, it's going to have a partially negative charge. That's what that weird symbol means. It looks like a cobra kind of biting its own tail. Okay, that's a partially negative because it's got the electrons really close to it. And because hydrogen has the electrons further away from it, we consider it to have a partially positive charge there. So this would be our dipole vectors with our partial positive and partial negative charges shown. So this would be the most correct way to show that we have bond polarity. So at this point, you have now done everything you need to do content-wise, and you are going to go through the rest of your guided notes. You're going to answer the rest of the questions. If you would like to, we also did the Lewis dot structures in class, and at this point you can draw Lewis dot structures for the rest of the double and triple bonds. Like I believe there was O2, there was N2, there was CH2O, there was a couple that we didn't get to. So you can go back and you can draw the ones that have double and triple bonds in it on that worksheet as well. But the entire guided notes packet should be completed for the rest of your homework.